cloud. I'm going to start sharing my screen. I'm going to first look at, today we're going to do not or odds. Hopefully we'll get to look at conditional. That homework 10 is due by the end of the day today. Homework 11 and 12 tentatively, pardon me, are due on Monday. I'm not that sure about homework 12. Somebody stopped me 2 minutes before the end of class to revisit where we are. There is a quiz that's in my labs. There's a Dropbox in Blackboard. It's only 2 questions, and they are 2 questions like on that handout that we went over for probability with permutations and combinations. And they're similar to questions from homework 10. I have gotten already requests to look at some of that homework 10. So I am going to go through, and we can't do all of them together, but we can do a couple of them together. And so if I preview homework 10, does anybody have, well, if the computer lets me preview homework 10, let's try that again. Yeah, well, it came and went. There it goes. Does anybody want to look at any of those questions in particular?
Number 4, maybe.
Number 4, okay. Let me try this again. Right now, this touch screen and I are not friends. So we'll just page over. 4 says a box contains 15 transistors, 3 of which are defective. If 3 are selected at random, find the probability of the statements below. All are defective. Well, the probability I have to apologize. Oh, I know why it's not letting me write on the screen, because I'm not using a pen. Hello. The probability that they're all defective is equal to the number of ways I can get all defective over the number of ways I can pick 3. Well, when I'm taking those transistors out of that box, does order matter? I don't
No.
know. It doesn't matter to me which came first or not. So I'm going to use combinations. Well, there's 3 defective, and I'm picking 3. So wouldn't that numerator be 3 combination 3? And then the denominator, well, if I'm picking just any 3 from the box, wouldn't that be 15 combination 3? Does that make sense?
Yeah.
Okay,
Yeah.
are you all right if we just set them up and don't do the computation? Are you okay finding those combinations from your calculator?
Yeah.
Then if I want the probability that none are defective, wouldn't that be the number of ways I can get no defective ones over the number of ways I can pick 3? Wow. Well, the number of ways I can pick 3, we already said was 15 combination 3. Numerator is going to be combination 3, but I'm picking from the ones that are not defective. Well, how many are not defective? If there's 15 altogether, 3 are defective. Doesn't that leave 12 that aren't?
Yeah.
And so does it make sense that this numerator then this time would be 12 combination 3?
Yeah.
Mm-hmm.
Better?
Yep.
Okay. Were you all right on your own with setting up the first one?
Oh,
I think-
yeah.
I think what makes this one tricky is to realize that if 3 are defective, then 12 are not. Okay? What other ones do we want to look at?
Maybe number 6.
Number 6 says a hand consists of 3 cards from a well-shuffled deck of cards. Find the total number possible of 3 card poker hands. Well, we jokingly said, like Cookie Monster, C is for cookie, C is for cards, C is for combination. So we know it's a combination. All of the number of hands, there are 52 cards, and I want to choose 3. Are you okay if I just set that up and don't look at it?
Yes.
Now, how many ways can I pick all red cards? Well, my deck of cards hits 52. Is everybody all right? Half of them are red and half of them are black. And so if I think of taking that 52 and dividing it by 2, it tells me that there are 26 red cards. So the ways of getting just a red card, well, from those 26 cards, I'd be choosing 3. So far, so good.
Yes.
And then for part C, well, then what's the probability of picking 3 red cards, getting a red flush? Well, wouldn't that be the answer from B, the number of ways of getting 3 red cards, over the answer from A, the total number of ways of getting 3 cards?
Yep.
Okay, that one better.
What is the answer?
Well,
All of them?
For part A, I apologize. I was being lazy and I wasn't doing the computation. For part A, if I do 52 combination
3.
3, I get 22,100. For part C, if I do 26 combination 3, I get 2,600. And so part C would be that fraction, 2006. I am so sorry. I have no idea why. All of a sudden, when I try to write using the Zoom pen, it won't let me make curves. Let's see, 2,600 over the 22,100. And then you'd have to reduce.
Okay.
Okay, better?
Yes.
Okay. What else do you folks want to look at?
Number 8, if we still can.
Okay. And then if everybody's all right, we'll call number 8 the last one that we look at. Whoops, I gotta turn my finger back into a mouse. You're dealt 3 cards from a deck of 52. Find the probability of getting 2 queens and 1 king. Well, first of all, it's probability. So I'm going to have a fraction. The denominator is going to be all of the ways I can get 3 cards from the 52. So I think we've reasoned through already that that would be 52 combination 3. The numerator will be the number of ways I can get 2 queens and 1 king. Well, how many queens are there?
4.
4. So wouldn't that be combination from 4, choose 2? There are 4 kings. For the kings, from the 4 kings, I want to choose 1. What we need to remember now is that counting principle says if I want the ways I can pick those queens and those kings, Counting principle told me to multiply those answers. Setting it up, okay? Is everybody all right using your calculator to get those numbers and plug in?
Yeah.
Okay, a little bit better feel for these. Did that help?
Yes.
Mm-hmm.
Okay, the quiz is going to have questions similar to some of these. So, that having been said, I'm going to turn my finger back into a mouse. I'm going to clear the drawings and I'm going to go and, oh, no, not there, there. I'm going to go and look at the notes. We looked a teeny tiny bit at this next section on Wednesday. And on Wednesday, we had said that if I wanted to find the probability of something not occurring, if I want to find the probability of not an event, we said that that would always be 1 minus the probability of the event. And so let's look at one more example. Let's say we want to find the probability of not getting a number card. When we pick one card from the deck. Well, if you had a deck of cards in front of you, it's 2 through 10 in each of the 4 suits. So there's 36 numbered cards out of the deck of 52. So the probability of getting a number card is 36 out of 52. So the probability of not getting a number card is 1 minus that. We said if we think of that one as 52 over 52. I'm sorry, that's not 13, that's 36 on this row. We get 16 out of 52. And then dividing both of those numbers by 4, that would reduce to 4 13ths. Does everybody remember that idea of not? The probability of something not occurring is 1 minus the probability that it does occur. Can I put a smiley face next to that idea? Are we all right with that?
Yeah.
Great. Then next thing we're going to look at is that word or. And in order to come up with that word or, we have to define first mutually exclusive events. And mutually exclusive events are events that have no outcomes in common. And so, for example, if I have a deck of cards, I want to pick one. I want to know what's the probability I get a king or a jack. First of all, is everybody all right with the idea that kings and jacks are mutually exclusive? No jacks are kings, no kings are jacks. They have nothing in common. If I ask for the probability of a king, am I just talking at you? Well, is everybody all right? That probability would be 4 kings out of the 52 cards.
Yeah.
So what would the probability of a jack be?
4 out of 52.
4 out of 52. So there are 4 kings, there are 4 jacks. None of them are the same cards. So does it make sense that the probability of a king or a jack would be 8 out of the 52 cards?
Yeah.
And so we're going to say that if A and B are mutually exclusive events, oh, how do you spell exclusive? Then the probability of A or B is the probability of A plus the probability of B. If I see the word or, it's loosely telling me that I'm going to add. So let's look at another example. Let's go back to that deck of cards. Want to pick one. You want the probability that it's a face card or an ace. Okay. We said aces aren't faces, so faces aren't aces, so they are exclusive. So if I want the probability of a face, let's see, that's king, queen, jack in each of the 4 suits. So that's 12 out of the 52. The probability of an ace, that's 4 out of 52. So putting those together, the probability of, I'm getting lazy here, a face or an ace. Are you guys all right if I draw a face?
Yeah.
Is 12 50-seconds plus 4 50-seconds, which gives me 16 over 52, which could reduce to 413. And if I see that or, I'm going to add. But I'm going to put an asterisk next to that idea of or telling me to add. Because sometimes it's a little bit more complicated. Is everybody all right if I turn the page, or do I need to wait a minute? We all good?
Yeah.
So let's do another example. That same deck of cards that are well shuffled in the whole dealio. You want to pick one. What's the probability of a heart or a queen? So the probability of a queen, how many queens are there
4,
out of
52.
the probability of a heart? How many hearts are there? Quarter of the deck?
13.
So that's 13 out of 52. But here's where I got issues. Are those mutually exclusive?
No.
No, why not?
Because it doesn't add to 52.
1 heart, 1 queen heart.
Yeah, isn't one of the queens, one queen is a heart? And 1 heart is a queen. So we're counting that twice, right? You can't count that same card twice. That doesn't work. So we're going to say that if A and B are not mutually exclusive, probability of A or B will equal the probability of the first one minus the probability of the second one. I'm sorry, plus the probability of the second one. I apologize. My head is ahead of my hands, and so it's all mixed up. Minus the probability of both occurring at the same time. So what the hell does that mean? If we look at that example, the probability of a queen or a heart will equal the probability of the queen plus the probability of the heart minus the probability that I have a card that's both a queen and a heart. So the queens are 4 out of 52. The hearts are 13 out of 52. But that one card is getting counted twice. So we have to subtract the probability of getting that one card. 1 out of 52. And this is real similar with what we did in sets. This mimics. Well, let's finish the problem and then I'll go and show you what it mimics. 4 plus 13 is 17 minus 1 is 16 out of 52 would be my answer. And this is very much like, you remember when we were counting the number of things. Sorry about that. In a union B, remember union is like the OR, is equal to the number of things in A plus the number of things in B minus the number of things that they have in common. And we're applying that rule to our events when they're not mutually exclusive. So let's say, for example, I roll a die once. I want to find the probability I get an even number or a number less than 4. And again, hopefully everybody remembers when I roll my die, my sample space of the numbers 1 through 6. And sometimes I find these things easier to work out if I actually have that sample space in front of me and I can see it. So my sample space are those numbers 1 through 6. So oh Lord, I'm sorry. The probability that I get an even, well, there's 6 outcomes. How many of them are even?
Your screen changed.
You can't see what I'm writing on anymore?
Well, now we can.
Okay, yeah, I have to apologize. What happened was my, the surface slipped. And when I tried to pick it up, I must have hit one of those buttons on the bottom of the screen. So what's the probability of getting an even number? How many of those 6 are even?
3.
Beautiful. What's the probability that I get a number less than 4?
3.
3. And then we have to find the probability that there's an even that is less than 4. So how many of the numbers less than 4 are even?
1.
1. So the probability that it's even or less than 4 would be that 3/6 plus that 3/6 But then we have to remember to subtract the overlap. Nothing counts twice. And so my final answer would be 5 out of 6. And so what you need to remember when you look at probability with that word or is that we add the probabilities, but we always have to stop and think, is there anything that fits in both? Is there any overlap? Is there anything we're counting twice? So let's do one more example. Can I turn the page and not lose anybody?
Yeah.
Example, let's say we have a deck of cards. We're gonna pick one. What's the probability? It's a red card or a face card. And I'm gonna be quiet for a minute and let you guys work on this one. I'll give you, well, I'll give you 2 minutes. Ellen, you came in, didn't you? Are you in there? How did I do? Did anybody else get 813?
Yeah.
Yep. Any questions? Do we need to add any details? Are we all ready to move on to the idea of odds?
Yeah.
Then looking at odds. Have any of you heard of odds? I know usually when I think of odds, I think of like around the Super Bowl, there's always what are the odds that this team wins or that team wins, or when they have any of those big famous horse races, Kentucky Derby and the like, they're always saying, what's the odds of this horse versus that horse? What are their odds? And when they talk about odds, they talk about it like a ratio. And odds, a lot of people use odds interchangeably with probability, but they are not the same. If E is an event, we're going to talk about 2 different types of odds. The odds in favor of E is the ratio. And does everybody remember a ratio was kind of like a fraction, but rather than writing it up and down, it's usually written sideways with a little colon in between. It's the ratio of the probability of E to the probability of not E. and the odds against the event E is the ratio. We're going to reverse it. The probability of not E to the probability of E. And so in order to find odds, we have to find the probability of the event. We have to find the probability of the event not occurring. And remember, that would be 1 minus the probability of the event. And then we have to write a ratio and simplify. So, what the heck does all of that mean? Does anybody need for me to be quiet for a minute so you can get this all down before we look at an example? Or are we ready to roll?
And just 1 second.
Sure. That's one of the things that I really miss about in-person classes is I don't have to bother you guys with a question like that. I can just look around the room and see what you're doing. But if I'm sharing my screen in Zoom, I can't see you folks. And also most of you choose not to turn your cameras on. Can we do an example now?
Yes.
Yeah.
So let's say we roll a die. We want the odds, first of all, in favor of getting, let's say, 3. So on a die, what's the probability of getting the number 3?
1 out of 6.
Beautiful, I love it. So what's the probability of not getting a 3? Well, that would be 1 minus 1/6, which is everybody all right, would be 5/6.
Yes.
So then the odds in favor of a 3 is the ratio 1/6 to 5/6. But usually when you see the odds written as a ratio, it's a ratio of whole numbers, not fractions. And so when I do this, I work my damn hardest to not reduce to begin with. And because they're the same denominators, it equals just the ratio of the numerators. So that 1/6 to 5/6 will simplify to the ratio of 1 to 5. So before we go further, I want to take a minute and just make sure that everybody notices that the probability and the odds are both different. Do you notice one is 1/6 and the other is 1 to 5? They're different values. Now instead, if I asked for the odds against 3, I'd put the not 3 first. So it would be 5/6 to 1/6, which is 5 to 1. Does anybody notice that the relationship between odds in favor and odds against is just I flipped them. And in this mind, it puts my mind, pardon me, this puts an exclamation point after the idea that the odds is very much different than probability. Because you know how we had said that probability is always smaller than 1? This number is much bigger than 1. That would be like the number 5 over 1 or the whole number 5. And so odds can be bigger than 1. If something's more likely to happen more than half the time, the odds will be bigger than 1. If something's likely to happen less than half the time, the odds will be smaller than 1. So let's look at another example. Let's go back to our deck of cards. Let's pick one. Let's find the odds in favor of getting a face card. And I'm going to be quiet for a minute and ask you guys to find for me the probability of a face, the probability of not getting a face, and then set up that ratio to find the odds in favor of a face. So, did everybody get that ratio be 12 to 40?
Yeah.
Now, that 12 to 40, I can think of the fraction as the fraction 12 over 40, and that fraction would reduce to 3/10. So the reduced form, the simplified form, would be the ratio 3 to 10. This one, okay.
Yeah.
Now, we also have to work backwards. And so I want to look at the odds being 12 to 40 and compare that to the probability of 12 over 52. You notice how the first number is the same as the numerator. And what happens is that denominator in the probability is the total of the two. So to work in reverse, if the odds in favor of an event is A to B, the probability of the event is the first number A over the denominator would be the sum of the two, A plus B. So let's say, for example, in a game, the odds of winning are 2 to 5. What's the probability of winning? And again, if my odds are A to B, the probability is their first number, A, over, in the denominator, I'd have the sum of the two, A plus B. So here, the first number is 2, and the sum would be 2 plus 5. So the probability is 2/7. Okie dokie?
Yeah.
Great. Then we've got 5 minutes. I don't think we'll get fully through conditional probability, but we can do a little bit of definition-y start. So going back to the first page of the notes, assignment 12 will not be due on Monday. I'll kick that can down the road a little bit. But in order to discuss conditional probability, we need to know what it means for events to be independent. Well, in life, if two things are independent of each other, doesn't that mean they really don't have anything to do with each other?
No.
So if they're independent of each other, they don't have anything in common, or we're going to say independent events. We're going to say two events are independent if the occurrence of one has no effect on the occurrence of the other. One doesn't influence the other in any way at all. So for example, if I toss 2 coins, first coin's going to be either a heads or a tails. Second coin's going to be either a heads or a tails. But what happens on the first coin? Does it have any effect at all on what happens on the second coin?
No.
No, they're independent. And so if I toss 2 coins, if I want to find what's the probability they're both heads, well, for the first coin, the probability of a head is a half. For the second coin, the probability of a head is a half. And if I want them both heads, that would be like a probability of a head and a head. So I'm going to just multiply 1/2 times 1/2 and get 1/4. So if A and B are independent, the probability of A and B will be the probability of A times the probability of B. So another example. Let's say I roll 2 dice. What's the probability? They're both 1. Well, what happens on one die, what side ends up face up on the first die, has absolutely nothing to do with what happens on the second die. So that would be the probability of getting a 1 on the first one and a 1 on the second one. So that would be 1/6. The word and tells me to multiply. And that gives me 1 out of the 36 possible outcomes. And now looking at where we're going next, it won't fit in a minute. So are you folks all right if we stop here today?
Is
Yeah.
the quiz, the quiz is gonna be on this and proper road.
No, the quiz is going to be, give me a second. The quiz is going to be 2 questions like homework 10. It's not going to be, I promise I'll never give you a quiz immediately on something that we learned. That's what the
Okay.
homework is for you to practice and get the bugs out before you get quizzed or tested on it. But we've spent a bit of time on the content of homework 10. So the quiz is going to be 2 questions like those on homework 10.
Okay.
Okay?
So just study the homework 10? Is
Yeah.
that-
And that probability practice handout that we had. Okay?
The very first one, right?
It was we started that handout on Monday and finished it on Wednesday.
That's the one with the cards.
Yeah, with the cards and the candy and the teacher picking on the kids and things like that. Okay?
Okay.
All right, so I'm gonna stop sharing.
Oh, I noticed the video from the 19, it didn't load.